this is sort of a way to see how the kinematics of a high energy scattering process, this I will simply not worry about, and you can write here k squared plus k perp squared over q square root 2 to get everything working, but nevertheless that's 0 as compared to the others. So this 0 now works. And I have made no assumption on this momentum except that it originates from this side. So, but the this thing is actually a very interesting one because it tells me that no, let me not write it as a delta function. It tells me simply that x is xBjorken. And that's actually I spend a lot of time on it, but this is what is happening in many processes, be it Radian, deep inelastic scattering, or whatever. You essentially have a momentum P, you have another momentum Q, or in Radian you have P1 and P2. You know that these are hadronic, these have certain properties, like that the q squared is q squared, and in this case that one has to be large and the other is small. You essentially see now immediately that this thing is okay, so this thing is fixed. And that's essentially how this system talks to the final state. And in the initial state, nothing happens in the final state because it has all the momentum has to go in this component, because otherwise it will not work. No momentum has to go in this component, otherwise this thing could not be solved. I mean, it's either in the final state jet, which is k squared equals 0, or it is an element or a parton which goes into a fragmentation function, but then just as these arguments, all the momenta also should be of hadronic size. It should be described, say, the collinear soft physics of fragmentation or of distributions. And so now, essentially, this is telling you that the initial state only talks to things through the plus component, through the collinear fast direction. Proton has a fast direction, that's the plus direction, and the plus coordinate, and it essentially has to eat the plus component of this. So that it has to eat the plus component of this tells you that this momentum, since these two, that's a kinematic variable, xb as I defined it, just has to do with this momentum and that momentum, but this and that has to become that, and then nothing else. And so you have this this situation, and this tells you that this thing has to be this. And this is just to get the kinematics right. Okay. And this is precisely what was underlying my description yesterday. I say P is essentially xp. Well, see here, xBjorken is this, so this, something is not working. This has to eat that, so there should not be a 1 over x. I haven't. There should be, to get this working, this should be, no I did it, there's another, no, there's two already, so, no I did this, you should take care, I mean, you didn't know I made an error, Yeah, okay, the x was just introduced, but the right way to introduce it is x over xb, and that's how I introduce it. I mean, I can introduce it as I wish in some sense. Still, it is x, pt, and p squared as the three variables. Now, still everything is it. But as I said, this plus that has to become 0, and so now I see that this is this, and then it tells me that the small p, that this x is indeed just, if you want, the fraction of this of that. More in coordinates, x is essentially, say, the light cone fraction of small p plus over capital P plus. That's the essential thing in this identification, and that's the way the system talks to the hard part. And that's why, if you want, at some point x is going to be the very in this phi, which can also be written as a phi of x and pt, and in principle of p minus, say, or p squared, or p dot p. I wrote it as p dot p. So that's this thing. This thing is irrelevant. That's the first component, the p minus. The x has to talk to the hard part and has to be identified with the Bjorken scaling variable, and then the pt is left. And the value of pt doesn't matter for all of these arguments, because this is much larger. So this is fixing the kinematics and identifying the fraction of momentum with the Bjorken scaling. Yeah?
And there is no constraint on the transverse momentum part in the P. So kt and the p.
These arguments should, they only work essentially if pt squared and p squared both should be, but there's a relation between p squared, p dot p, and pt squared. So you can, and then pt squared also has to be small. So again, exercise. Write down the relation between this thing, and pt squared, and what you will see is that this relation is essentially that it's a linear relation which has certain coefficients. X comes in, m squared comes in somewhere, but all three of them have to be of the size of the hadronic size, not larger. I mean, this requires at some point a choice of reference frame, a choice of fast direction. In this situation, the fast direction naturally is given by P and Q. I mean, you sort of have a P, which, I mean, in the rest frame there's no preferred direction, but now it's hit by a photon, and this photon has a hard space-like direction. So now you have your space-like direction, and essentially by making this choice, I chose the space-like direction to be the z direction, because this essentially, the sum of these two is 0, and the sum of the 0 and the 3 component is essentially the z component. No, the diff, with the minus sign I made sure that this defines the z direction. Yeah? Because the minus z direction, the z direction is along the proton, the minus z direction is along the photon in this choice. Actually, there's a whole convention in the literature, which is, I mean, some people choose the photon along the plus z direction, and some people doing deep inelastic scattering choose the photon along the minus z direction. But in fact, you shouldn't worry about it. Do it like this. You do worry that later on, of course, there is plus pt, plus even something else, and this something else is the minus component. This pt is that component, and that's the p plus, and it's along p. Now the nice thing is, after writing this, is what I also say is, of this d4p integration with these coordinates, immediately you can do one integration, and so what we are left with is a phi of x and pt. It has an intrinsic dependence on the choice of the n, when the n is essentially usually standing also for the n minus, it's the minus direction. The choice of which direction is this, or which is the transverse direction, because after you have fixed the plus and the minus direction, of course the transverse direction is fully fixed. It's transverse in this situation with respect to the proton and the photon. But you could have chosen it transverse with respect to this and later on a produced hadron, but that's a choice, so there is a small choice here. That's, I already tell you, that's not going to be relevant in any leading order expression. This choice is going to be relevant if you ever extend this formalism to what is called twist 3 and go to subleading 1 over q corrections. Then this is going to be extremely relevant. But that you look very carefully at this choice of n. But you can treat it. So now what we do is, we say this minus component is irrelevant, because the half process doesn't talk to these small things. It doesn't matter for energy momentum conservation if this thing is there or is not there. So as far as evaluating this diagram, what you do is you say what can be done is you integrate over P minus, and then you realize that this is P minus psi plus P plus psi minus PT psi t. And what you see is that this is then the integral not over psi, but only over psi plus, because you integrate it over P minus. So psi, no, then it's only over psi minus, because a delta function over P minus will turn psi plus into a delta, will turn the thing into a delta function of psi plus. So essentially this is psi minus, psi t, d2 psi t. One of the two pi's is needed to put it into a delta function, and then you have left e to the I p dot x, p dot psi, ps, psi j 0 bar psi I psi p of s, but you have one delta function, you have one integration s, and the coordinate that you have, that the integral over P minus gives you a delta function of psi plus, you use that, and you have only 3 integrations left here, and psi plus is equal to 0. So that's essentially the thing now that you say, I have a correlator. It's now a sensible correlator. So this is my unintegrated, as it's called. You could say, if you want, this is fully unintegrated. I mean, it's everything, all non-locality between these fields. Here, this is still called unintegrated correlator, and this is, and it gives you the unintegrated PDFs, and these are called the TMDs. So the TMDs are the functions when you start saying this is equal to some functions, and divide it, f and pt squared, and then some structure. What would be the structure? Something maybe like p slash plus m or whatever. Now m is of course an irrelevant variable, so p slash. But p is of course the running variable, so take the protein, capital P plus p slash. Because this has Dirac initials, so they must reside somewhere. Now this I'll come in a minute. I'll show you that in more detail. So let me erase it here again, just for those that you later on recognize it. This is the object that one is going to parameterize. The nice thing of this object is also that it sits at psi plus equals 0. Now that solves another problem which some people should already have mentioned here. Why ever could you do this separation? Now, first of all, I had already the kinematic arguments, and I already gave you the solution of it. After we have done everything, we should later on check that indeed this momentum can never become large. I mentioned that, yes, you do later on the calculation, and you see that it falls off like alpha s over pt squared, so that the tail of these correlators indeed is not that important. And we were left with a semi-importance that 1 over pt squared is non-integrable, but this one Atterelli-Parisi problems, and you can do that. Now it solves a second problem, because this whole thing is of course is what the S matrix is. Now, and the S matrix is, as you from field theory may remember, how do you calculate? It's a time-ordered product of lots of fields. Yeah, that's what it is. I mean, you need the 4-point function, the 10-point function, or whatever. These are the time-ordered products of whatever fields you have available. How do you do that? By writing down all Feynman diagrams that you can invent, and then you have your time-ordered product. Yeah? And of course you need the right function, but the right function in this case is a bit hard, because I don't know which endpoint function I need. Because the proton can absorb 10 gluons and 4 antiquarks and whatever, and 5 quarks or something. Then I have 1 quark in the proton. Yeah, so that's it can absorb everything if you want. And that's essentially what is sitting in here. But then still all these fields are time ordered. But now the kinematics saves me, Because the kinematics tells me that the matrix element, as far as this blob is concerned, so this lower part, so as far as that part is concerned, that the matrix element is dead. And this is already time ordered, because it is at equal time. And that's time ordered. Okay, that's perfect. Now, you say, is it equal time? Is it equal psi, is it psi plus equals 0? Yeah, but Dirac told us, you should read that paper of Dirac, Forms of Quantum Mechanics. Dirac has told us that why would we use time t0 and then evolve t0? To get the whole physical region, you can as well start at x plus equals 0, and then let x plus grow, and then you essentially don't violate causality. I mean, you always go to larger times if you want. Go to larger times, or in other words, time ordering gives you these theta functions of time, and you can rewrite the time ordering rather than in x0, you can also do it in x plus. Yeah? So you can use the plus coordinates and time order them. And now, we are here at equal to x plus, so all matrix elements of these correlators, even if later on we are going to include things with quarks and gluons, they are already time ordered because they are at fixed psi plus equals 0. And that's what the kinematics forces upon us. Okay, problems with that? So that's the beauty of this thing. Now, of course, if this would be the process under consideration, you see that this thing is that, I mean, a fixed effect, there's no choice. I mean, if this would be a final state jet, and it would be deep inelastic scattering, so no particles detected in the final state, essentially, this tells me that this is equal to that, or in other words, that this variable in the delta function and that I essentially work in phi of x. Phi of x is the integral over just psi minus over 2 pi. I integrate over pt because it's I mean, any pt has to be taken into account in this d for p, but p doesn't talk to the hard part. It just is transferred to the final state, and there it wiggles a little bit in that direction, in that jet that is produced. And essentially, so this tells you that you have now e to the p plus psi minus, that's the only thing left, p as psi bar j0, psi I of psi, p of s. And now it is at psi plus equal, psi t equals 0, and a little bit of calculation tells you that then also psi squared is equal to 0, so now you are on the light cone. So these are nicely light cone matrix elements, these are light front. I mean, in the well-known this thing, the one is sitting on here and the other is sitting there. Is at the origin is essentially psi squared equals 0, and the other one is on the light cone direction. But that's these are the type of correlators, and it's this one. That's the only one that's accessible in deep inelastic scattering because PT is not relevant. But as soon as you now also start doing semi-inclusive deep inelastic scattering, or Drell-Yan for that, you have two hadrons involved, and Drell-Yan is then essentially that the hadron is in the final state, but in this situation, that this thing is here, and that it again also does something and produces as a hadron with momentum capital K, then you have to do this same sort of game here, capital K essentially is equal to, and then essentially, because so far you didn't have anything, and then this has to talk to that, and it has nothing here, so it must be sitting over here. Now, and then you say, this produces me a fraction z of the outgoing quark, so you introduce z, which is the light cone fraction of the produced hadron with respect to the full jet momentum, if if you want. So this is the fraction of the jet carried by, say, a pion. So you introduce that. This, of course, is mk squared plus, I mean, now it depends on if you put some momentum here or leave it. And what you could do is put this equal to 0, that equal to 0, yeah, but then you cannot put this thing to 0. So that frame I usually refer to in my notes as t. Then I have made a choice that that's 0 and that's 0. I can only put two things to 0, but this doesn't matter. It's divided by q. And again, what I see is that fragmentation only talks through one coordinate with the hard part, and that the other is irrelevant. But if you have these things, so if you have TMDs, if you are at this level, then you have, first of all, still that z is fixed by this kinematics. So z is essentially given by, I should put that on that blackboard, but let me first put it here, because then I can also put my exercise. We have seen that x is p plus over p plus, and z is essentially k minus the produced hadron. These are relations in semi-inclusive deep inelastic scattering over the minus component of the quark. Yeah? And that we have seen also that this is equal to, yeah, it could be equal to a lot of things, but one of the things is that this is equal to minus q plus capital P plus. And in the same way, you see that this is equal to capital K minus divided by the small k minus, that's this thing, is equal to the q minus. So that's q minus. So that's this thing. So these are the simple relations that govern all kinematics as far as the collinear thing is concerned. And then you're left with essentially that this plus that has to be, so you're always left in this d4p, which tells you that, which has also a delta 4 p plus q minus k, that's added to this, that you are left with a delta 2 function, because one of them is used to have the p plus and the q plus equal, and then the k plus didn't matter. One was used to have q minus and k minus, and then this one was not relevant, but for the transverse, everything is relevant. So through the transverse momentum, still such a soft part and such a soft part will talk to each other.
Sorry, in case of like so-called exclusive gradient,
Yeah.
then what would be the case for this capital K stuff? There would be no capital K, or?
In gradient there would be no capital, there would be only P1 and P2 to start off with. P1 would be one momentum and it would have plus momenta. P2 would have the minus momenta. You would have, just like you have a Q over X Bjorken, or Q over X1 if you want, you would have here a Q over X2 corresponding to P2, and then this would talk, and then everything else goes into Q, and then Q goes into your lepton pair. So that would be so it would be all the scaling variables would be in the initial state, and be determined by looking at the momentum Q. And essentially the momentum Q can have a free QT, which you don't know where it came from. And that's essentially what is left here. There's a delta 2 function left of the transverse momenta, and that in Drell-Yen is very obvious. You have P1 and P2 coming in, and then your photon is mostly time-like, but it can have some transverse direction, and you don't know if that came from hadron 1 or hadron 2. So essentially, this sort of the fact that always in the transverse momentum you're left with a convolution which involves one soft piece and another soft piece. And you now may say, yeah, but then we are lost because we have a hard part as is. No, let me tell you in a minute why we are not lost, because that's another part in the kinematics. So there is essentially QT as the transverse momentum variable, and in this situation we see what is left. If you give QT a variable, it is equal to KT minus PT. It's KT minus PT. Now, can experimentalists measure all of these things? Now, the first thing is, The first answer, or the answer is yes. Now, how do they measure this? Now, this thing, you can multiply this thing with Q minus and Q minus, and then you have Q plus Q minus, and that's Q squared. With the minus sign, it's precisely Q squared. You miss a factor 2, but that factor 2 I put here. P plus Q minus is P dot Q. No, you will say, P dot Q is P plus Q minus P minus Q plus PT Qt. Now, PT was equal put to 0 in this frame, that was my choice, so that's not a thing. And P minus times Q plus is essentially order 1, while the other thing is order Q squared. So the other one doesn't matter, and so this is 2P dot Q. So this is telling me, in other words, again, that x, that the momentum fraction in light-cone variables, is equal to the Bjerken scaling variable, because this thing was what was defined as the Bjerken scaling variable. Some people like to look at deep elastic scattering and don't determine the Bjerken scaling variable from the cube. You can also determine it from the outgoing jet. Let me show that. I said I multiply this with Q minus. No, I could have multiplied it also with K minus. Because K minus has the same sort of properties as Q minus, it only has one large component. And so then I get Q dot K over here, a minus sign, and I divide it by P dot K. Now, this, and any experimentalist can also measure that, and the result is, in a one-jet production process, is equal to the Bjerken scaling variable. I mean, this has, for people who worked at HEPA, or this has a name, I forgot the name, it's a way of determining X Bjerken just from the outgoing final state. So this, see this kinematic variable, and you can do the same thing here. You can multiply this thing with the P plus, and then you get K dot P over Q dot P. Any experimentalist can do that. This is what most people like to do, because look at this variable now in the rest frame of the proton. Then it's the energy of the produced particle divided by the energy of the photon. That's what most people use as the experimental variable ZH, the energy fraction of the particle produced in the final state. And it's equal to the light cone variable. That is what I have proven here. But some other people might want to determine it also from Q squared. And then I multiply this with Q plus. Again, that will give me 2K dot Q divided by Q squared, and then with some minus sign, because I need Q plus minus sign. So that's this thing. So this is, these are some kinematic relations that you can easily prove, and that depend, of course, on kinematics. The fact that you don't produce additional jets. If you start producing additional jets, you have to start modifying it. And if you say, I don't know if I produced a jet because you don't have the right jet algorithm or whatever, then of course you see the fact that higher PT particles are produced will start causing you to, will sort of urge you to be very careful. So this is a little bit playing with kinematics and saying to see the importance. Now let me say, can I now measure this thing? Now let's see what KT is. KT. Oh, here, then I go back here. KT is, it's equal to K. But then I should subtract this. But this thing is in fact the external momentum divided by Z. So this is equal to K minus D, and then I subtract the minus components minus K, the outgoing hadron, divided by Z. Now let's do for PT. PT is equal to P, and then I have to subtract this component, but that component is X times the proton. So I have to subtract minus P, and then minus the other component. Is there a